All right, so let's try this ideal gas law problem. So basically what I'm going to do is I'm going to take this little cloud of gas and I'm going to heat it up isobarically. The thing that's causing the pressure is this 15 kilogram mass, and it's going to stay 15 kilograms, this piston, the entire time. So it's providing the same amount of pressure as compared to the gas, right? So there's no reason for it to be any larger. It can't be any larger as long as this thing is on it. What I'm going to do to the gas is I'm going to heat it up, and then it's going to have a greater. It's going to increase the pressure. Then that's going to push this up until the pressure equilibrates. So that's basically what's going to happen. That's what's going to give us a higher energy. Now this is so that means this is 200 kilopascals. This is 200 kilopascals. Now this is the same piston as last time, so it's 14.7 square centimeters and 15 kilograms. We're going to start at the point where we were last time, where this was 10 centimeters, and see if we increase the temperature from 20 degrees C to 100 degrees C down here, whether or not that's going to get us any farther up than we started with. Remember, we put this guy on, we put the piston on when it was at 20 centimeters, and then we're letting it rise up again now at the with the temperature, and we're going to see how high that rises through the temperature. In an isobaric, that means same pressure setting. Last time we used an isothermal setting, and that allowed us to use Boyle's law. All right, so I've got two things that I want to look at here. One is how many atoms are in the gas. That's going to help me figure out the piston's new height. And again, this is an ideal gas law problem, so maybe I should write that out for you. You remember the ideal gas law. It's one of your favorite ones. It's PV equals NKBT. At least that's the physicist version. It's nRT for chemistry. And it's MR prime T for engineering. So it's all the same equation. It just depends on what you care about. Remember, what we care about is energy. So this is all basically the internal kinetic energy. P times V is the internal kinetic energy, and so is this, right? So Kb times T, remember T is the mean molecular kinetic energy. This just translates the temperature in Kelvin. Has to be an absolute temperature scale. It could be Reinke if you want, but nobody uses that, so it's going to be in Kelvin. And turns it into a joule in energy. And so that would be the average amount of energy per molecule in the gas. And then you multiply that by the number of molecules in the gas, that N, that gives you, the average times the number is the total, right? That's all it is. So you have the total internal kinetic energy of the gas. So both of these are the same thing. All right, so what are we going to do here? Well, we're going to just start putting numbers in. So we've got the pressure, which we are going to pretend is 200 kilopascals. And that's multiplied by the volume, which is 14.7 square centimeters, times the height here, which is 10 centimeters. That's going to be equal to the number of things that we want, right? That's the guy we want right there, times Kb, which is 1.38 times 10 to the minus 23 joules per Kelvin per molecule. And then I guess we need the temperature, and the temperature is 20 degrees C. This has to be in Kelvin, so that's 20 degrees C plus 273 K is equal to 293 K. So you have to add 273 to get from a relative scale, which is the centigrade or Celsius, to an absolute scale, which is the Kelvin. So we have 293 K. I probably should have done something to make that a little easier to see. Oh well. All right, so now we have to figure out what all this stuff is. All right, so here we have 2 times 10 to the 5th pascals, which are newtons per square meter. And then we have 14.7 times 10 to the minus 4 square meters. Right? And then we have 10 to the minus 1 meters. Right? 1 centimeter is 1/10 of a meter. And that's equal to n times 1.38 times 293. That's not an easy one, so let me ask this guy. That's 404.34 times 10 to the minus 23 joules. That's what we're going to call those. We're going to call those joules because they're energy. Let's see here. Okay, we've only got to multiply 2 by 14.7, so that's 29.4. We have 5 minus 4 minus 1, so it's actually just 29.4 joules here. So 29.4 joules is equal to 404.34 times 10 to the minus 23 joules. So joules are going to cancel, which is good. Because what we want is just a pure number. And so we have multiplied by n. So that's going to be 29.4 joules over 404.34 joules times 10 to the 23rd. Okay, so 29.4 over 404. That's somewhere around, I don't know, 0.07 maybe? I think that's right, so 0.07, so that means 7.27 times 10 to the, 221 atoms. So that's 7.27 times 10 to the 21 atoms. Let's see if I'm right. Oops. Hopefully this... Okay, so... I didn't fix that error on that slide. Oh well. Let's take a peek at this. So we're going to use the ideal gas law again now at a new temperature. So we're raising the temperature from 20 degrees C, right? So this was 293 K, to the new temperature, which is 100 degrees C, which is 373. If we add 273 to 373, or 273 to 100, we just increase that to 373. And so that's our new temperature. We have to go through this whole rigmarole again. So we don't know the new height. So the V is going to equal the area times the height. So we'll now have 200 kilopascals times 14.7 centimeters squared times the height is equal to, let's see, what's this, 7.27 times 10 to the 21st times 1.38 times 10 to the minus 23. That's Boltzmann's constant, joules per Kelvin, times this 373 K that we just talked about up here. All right, so let's see. This guy is just 10 times this guy, right? So this is 294. I probably should have done this farther to the left. Joules per meter, because we don't have that height there with us yet. Then we have all this other stuff. So we have 7.27 and 10 to the 21st and 1.38 times 10 to the minus 23. I don't know that. So that's 7.27 times 1.38. Okay, so that right now is 10.0, and there's extra stuff after that. Oops, 23. So this is 10 to the minus 2. So we have, let's go out. So we have basically 0.1003. We're going to multiply that by 373 Kelvin. Right, so that's going to give us something like 37 point, let's give it the 4 joules. All right. And so we just divide through by 294 on each side. 374, 37.4, 294. That's joules over joules per meter, which is in meters. So that's going to be no. You're allowed to do that to me. Um, 0.27 meters, or 127 meters, which is 13 centimeters. Okay, and I screwed that up here for some reason. I'm having a hard time believing that I screwed this up because I did it in Excel. But I can still screw up the Excel, right? And I screwed up the last one because I did it right. 12.7 centimeters. Yeah, that's what I said. Okay. So there it is there. So let's see, what did we do? Well, we just used the ideal gas law 2 times. We used 1 to figure out what n was, and then after we got n, we came over here and used that to figure out what the height was. And that's pretty much it. So this is just a important thing. So remember, the ideal gas law is the easiest equation of state. And I talked a little bit about some of the issues with that. If you had a more complicated equation of state, what would happen? In the previous example, which is the previous example for you, not for me. That's about it. There's not much more to do with this. So all you have to realize here is that you want somehow to have these things not changing, or not necessarily those things, but everything else doesn't change. You want to try to make only one thing change at a time if you can. You can do it for other things, but I don't think we want to do anything really complicated. So if I ask you anything, only one thing will be changing at a time as best as I can make it change, right? So one thing other than the thing that you're looking for. All right, so I think that is it for today, and I hope you're having a great time, and I will see you soon. Bye now.